Hello, this is question 5 from the 2018 MAT. So we've got n is a positive integer and n brick is a rectangle of height 1, width n. A 1 tower is defined as a 1 brick, and n tower for n is greater than or equal to 2 defined as an n brick on top of which exactly 2 other towers are stacked, a k1 tower and a k2 tower. K1 is between 1 and n minus 1 inclusive. K1 plus K2 is n. Good lord. The K1 tower is placed to the left of the K2 tower, so that side by side they fit exactly on top of the n brick. Right, that is more terminology than I would like to deal with at the start of a question. Here is a 4 tower. Right, let's try and unpick this. So a 4 tower. Right, so that's here, an n tower, so a 4 tower. N is greater than or equal to 2, right? It is because it's 4. An n brick, so that's 1 height, width 4. Right, so this is our n brick. That's our 4 brick at the bottom. Okay, and we're on top of that, we've got 2 other towers. So we've got a 1 tower in this case, which is the 1 brick, so that's that. And then we've got this, which must be a 3 tower, which has got 2 towers on it, which is a 1 tower and a 2 tower. Okay, fair enough. And they fit side by side, so they always have to fill up the width of the n brick. So we can't have a 1 and a 2 or a 1 or a 1 on here. We have to have a 3 and a 1 or a 2 and a 2. Right, draw the 4 other 4 towers. Right, this should be a bit easier now. 4 other 4 towers. So we have to have a 4 brick on the bottom. So we need that 4 times. We'll be able to just about squeeze this in, hopefully. Right, well, let's put this one on the left. Let's put the mirror image of that one. Put the 1 brick on that side, the 3 brick on that side. So that's a 3, 1. And then do a 1 and a 2. So 1, 2, and then 2 1s. Okay, so that's just flipped over what we've got there. Then, well, I suppose we could flip the 2s over as well. So we could have a 3 and a 1, and a 2 and a 1, and then a 1 and a 1. Right, so that's that. So that's done 2 on the left. So we must have the other one with a 3 brick on the right. 1, 3. This time I'll put the 2 on the outside. 1, 2, 1, 1. So this must be the one with the 2 bricks then. So we'll have 2, 2. And that's just going to be flat across the top. 1, 1, 1, 1. Right, so that's the 4 towers. What's the maximum height of an n tower? Justify your answer. Right, well, these have got maximum height of 4, which is n. Yeah, we're dropping by 1 each time. So we've got the maximum n brick reduces by 1 for each level. Therefore, maximum of n levels in n tower. Okay. The area of a tower is defined as the sum of the widths of its bricks. For example, the 4 tower drawn above as the area 4 plus 4 plus 3 plus 2 is 13. 4 plus 4 plus 3 plus 2. Oh no, just aggregated each level. Right, 4 plus 4 plus 3 plus 2. Fair enough. Give an expression for the area of an n tower of maximum height. So, well, we're always going to have that, aren't we? We're going to have 4, 3, 2, 1, and then we're getting an extra 1 on each level, except the bottom level. Yes, that's how it's working, isn't it? So we're going to be getting the 4th triangular number. So we're getting n plus 1 over 2 plus n minus 1, because we're getting an extra 1 on each level. So we've got 4, 3, 2, 1, and then 1, 1, 1. Okay, so we've got that. Do I need to do anything with that, or is that going to be sufficient? Maybe. Well, I'll just leave it like that, I think. See what happens. Show that there are infinitely many n, such that there is an n tower of height exactly 1 plus log base 2 of n. log base 2 of n. So we're going to be wanting n towers that are powers of 2. So we want to have so if we got n is 2, 4, 8, 16, then we want to have the height to be 2, 3, then 4, then 5. So we're doing that for our height. So how are we going to be doing this then? Show that there are infinitely many n. So if we can just keep on building these up in some kind of pattern. So for 2 then we have to have, well, there's only one option we've got. For 2, that's all we can do with 2s. And then for 4s, for height 3, all we can do is that one. That's the one that we've drawn out. So we've got a 4. And then, well, we've got 2 towers on there. So we're getting that. 1, 1, 1, 1, 2, 2, 4. Right, so if we want an 8 one, which has got height 4, then we're going to put 2 4 towers. So this is going to be a, yeah, okay, so that's our 2 tower. Well, I suppose I could have done the 1 tower as well. Might have been a possibility. It's just a 1 brick, isn't it? Then we're saying we've got a 4 brick with 2 towers. And then we've got an 8 brick with 2 times 4 towers. So we've got 2 4 towers on an 8 brick. So all we're doing, so we are increasing in height each time by 1. So yeah, height increases, therefore height increases by 1 each time n doubles. That's also our minimum height, but there you go. So we're going to have infinitely many, therefore can increase n infinitely, indefinitely. Right, so that's okay. What are we doing now? Part 5, right? Tn for the number of n towers, right? T1 is 1. Give a formula. Oh my word, right? So we need a formula for Tn. Right, how are we going to get the number of, I think I'm going to need a new sheet for this. It seems quite involved. So we've got the number of n towers. So there's got to be a pattern of how we're putting these things together. So we've got T1 is equal to 1. We know that T2 is equal to 1. So we're going from a 1 brick. Then all we can do with a 2 brick is that. We can't do anything else. 4 brick, we know. Oh, we haven't done the T3 yet. But we know that T4 is equal to 5. We've done that. So how many T3s are there going to be? So for a T3, we could do a 3 with a 2 and a 1, like that. So that would work. Or we could do a 3 with a 1 and a 2, like that. But we can't do anything else. So we've only got 2 options there. So 1, 1, 2, 5. Right, let's try and get a pattern then of how I'm actually putting together these 4 bricks and things. I don't know, maybe I'll put the 4 bricks. What do we have for the 4 bricks? Because we've certainly got should be sectioned off. So we've got a 3 there, 2 on one side, 2 on the other side. So every time we split it, this is the thing, it's got to be something to do with every time we split it, then we're getting the number of options that we've got here multiplied by number of options there. I mean, this is saying it's T2 times T1 plus T1 times T2. That's what we got there. So how would that then work? Here we've just done, it's too small on the previous one. Let's go back to the previous slide where I've drawn out all the T4 ones. See if there's a pattern here. So this is saying that we've got T2 times T2. And this would be a T3 times a T1. That would be, yeah, is that just coming out as it is? Because we've got, yeah, that is the, and plus T1 times T3. Does that then go the other way? It must do, mustn't it? Plus T1 times T3. Okay, so that means we've got 1 times 1, that gives us 1. That gives us 2 times 1 gives us 2, and that gives us 1 times 2 gives us 2, which gives us 5. Right, so that is what we're doing then. It's just how many ways can you permutate these things. So we're saying that Tn is, well, let's just write these things out again. So we're doing, if we were doing T5, say, then we'd be saying that is T4 times T1 plus T3 times T2 plus T2 times T3 plus T1 times T4. So that's what we're doing on this. So we've got one of them counting up and the other one counting down. And we're going from k equals 1 to n minus 1. We've got T subscript k, and we've got T subscript, is it n minus k? What are we going? We're going tk. So when we've got 4, well, when we've got 1, I should say, so we've got a T1 and we want to have T4. So n minus k. Yes, that works. And then we add those up. Right, okay. That's an ugly looking thing. But again, pattern spotting at its finest. Use your formula to compute T6. Right, so T5 then is going to be equal to 5 plus 2 plus 2 plus 5. Seems to be what we've got, doesn't it? So we've got 14. So T6 is going to be equal to 14 plus 5 plus 4 plus 5 plus 14. So 28, 38, 42. Right. Eek. Show that Tn is odd if and only if T2n is odd. Okay. So Tn is odd if and only if T2n is odd. Right. Well, T2n then is going to be the sum from k equals 1 to 2n minus 1 of tk t to 2n minus k. Right, so we've got that. I mean, that seems the only place to start. We haven't got anything else to go with here. And we want to have something to do with Tn, with this thing. So we've got Tn there, which goes from 1 to n minus 1. So it's a big chunk of this. So let's put that in there maybe. So T2n is going to be equal to Tn plus, so we've got rid of the first big chunk of this. So we're then going to be going from k equals n to 2n minus 1 of tk 2 to the n minus k. So I've just chopped off the first bit of that sum. Okay, so we've got something that is odd in there. Then what do we do? Don't really know where to go with this. Is this, so show that Tn is odd if and only if t to the 2n is odd. I mean, if we could show that this thing was even, then that would certainly help. because then we'd have to have an odd plus an even. You know, if t to the 2n was even and this thing is even, then tn would have to be even as well. So can we show that that thing is even? Does it have a multiple of 2 in it? Not sure it does really, does it? The 2n minus 1 how does this work if we're doing this? Does it come out as being, I don't really know where this is going. We're going to have tn, yeah, I don't know where this is going at all, because this is going up from where we want. We don't really want it going up from where we want. Or are these things the same in some way? Are these things the same? Because we'd be going t, yeah, because this is then counting down. So if you had n, so you'd have t, no, it doesn't really work, does it? You'd have tn, and then, oh, that's tn squared, the first term. And then we'd have tn plus 1 times tn minus 1. This just seems a bit of a mess, but I like this tn squared coming out of there. So maybe I want to go with that. That might be a better option, because that tn squared, we're going to then split. It's the middle of this whole sum is dropping out as being tn squared. And that's useful if tn is going to be odd. And then we've got two things. Right, let's try writing that out a different way then. So t2n then, what if I split that into the sum from k equals 1 up to n minus 1 of tk t to the 2n minus k, then add that tn squared bit in the middle, tn times tn, and then have the rest of it afterwards. So this is going from k equals n plus 1 up to 2n minus 1 of tk t to the 2n minus k, because this is really useful, having this tn squared. So what, actually these might be the same now. If we were doing these, what would these k's and things look like? So this left hand sum would be going t1 t2n minus 1, t2 t2n minus 2, t3 t2n minus 3, and then the right hand sum would be going t2n minus 1 and then t1 t2n minus 2 and t2. Yeah, so this is going up exactly. These are the same. These are the same sums. So that and that are the same thing. So this then, let's go back to blue, is going to be tn plus 2 lots of the sum from k equals 1 to n minus 1 tk t to the 2n minus k. Okay, so therefore then we have got that if t to the 2n is even, then we've got tn times tn is even, as in even equals even plus even. And if tn is even, then we can say therefore tn is even. We need to do a similar thing. So if you had space at the bottom of the page, just keep it right in there. We can say if t2n is odd, then tn is odd for the same reason. Odd equals odd plus even. Therefore, tn is odd. Right, okay, that was another stabbing in the dark one. It was only when this came out, this tn bit, that it became apparent. I mean, I can't really see a way of getting that and showing that it's definitely going to be even. I mean, I suppose well, I mean, this thing is tn as well. So, but we need to show that these things are the same, don't we, at either end? If we don't get that the coming down from one end is the same as coming up from the other end, then we can't say that we've got two lots of these. I mean, I suppose that's another thing that we've got in all of this. That's just saying we got 2tn plus tn squared. But still, it all comes out the same way. But yeah, you have to be able to spot some way of finding something that's even and then a statement about tn. And this just ended up being a bit of a dead end unless you can see a way of unraveling what's going on with this particular sum. It's not obvious to me what to do with that. But fortunately, this dropped out anyway. Another way of getting a handle on tn. I would say that last part was extremely difficult. So of this overall, first part was fine, second part was fine, third part was fine, fourth was okay, but maybe hard to put into words, but it wasn't that much of a problem. Five was, that five wasn't that easy, but it's pattern spotting. So once you start going through, just keep building it up until you see the pattern. Then it was fine, and six was just really, really unpleasant, which is fitting this paper being a difficult paper. There just haven't been many easy questions in this. So yeah, I'd imagine that the marks were lower this time, certainly compared to last year, the 2017 year. Anyway, another one done.